Um, thank you for joining us at this seminar on collective intelligence. It's being organized. I'm Geoff Mulgan. I'll be chairing it on behalf of the other editors of the journal, and who are Panos Iperioutos, Scott Page, Jessica Flack, and Tom Malone. We're going to have this will be the first of a series we'll run every 2 or 3 months, showcasing some of the work done for the journal. I hope that some of you participating will be prompted to submit papers, ideally interesting research, case studies, perspectives, and so on. We've had fantastic articles so far. I hope you've all had a chance to look at the journal. The next sessions will be June the 16th and September the 14th. If you follow Collective Intelligence Journal on Twitter, you will be able to keep on top of those. I've just had a raised hand. Is that for could you maybe put in chat if there is something you want to raise? We're going to have a series of fairly rapid presentations, and then there will be time for some comments or questions. We'll look at any overlapping topics and perhaps any disagreements as well as agreements. And I hope that over time with these sessions, we will help to grow a community of people interested in all of these topics. So our first presentation is going to be from Richard Mann. I hope you are ready to talk and share your screen, Richard. Thanks.
Yeah, let's try and share them. Yeah. Hopefully you can see that.
Yeah, that looks good. Thanks.
All right. Excellent. Am I ready to go then?
You certainly are. Yeah.
Okay. So I'm going to be talking, as Geoff suggests, in a very rapid fire way about a paper I published in Collective Intelligence a couple of months back now, with this rather unwieldy title, which hopefully will become clear as I go through. So what I was interested in this paper is looking at how rational agents should use social information, and in particular, how the nature of the social connectivity that the agents are sort of embedded in changes how they should use the social information that they can observe. And this can be sort of illustrated by using a network. So you could have an agent which can perceive relatively few neighbors, but in a fully connected network. This might be, for example, in a small network of friends. And the way that that individual should use the information it perceives, such as one person expressing opinion A, another person then expressing opinion B, and so on, is different than if the agent sees the same amount of social information, but it's embedded in a much sparser environment. So maybe it goes out into the world, meets one random person who says A, then meets another random person who says B, and so on in some sort of sequence. And so one part of the paper was calculating what the rational thing for the agent to do is, conditioned on what it's observed, so the sequence of opinions that it has observed others make before itself, on the assumption that it's trying to sort of express the correct opinion itself as a function of this connectivity. And what we see in the illustrations here are the ways in which that is different for the sparse and the fully connected case. So at the top, you have the fully connected case, and there you see 2 plots. One is how much I should expect that the agent will express A, given that it has seen, say, 8 individuals say A and 2 say B, for example, as one point on this plot in the top left. And you see this sort of radial pattern of contour lines, which shows that this sort of varies with the proportion of individuals who've already expressed an opinion. And then we can condition on saying, well, what happened if the last person said A. So they saw some sequence, but the most recent one was A. And there we see that the pattern changes quite considerably. In fact, they become very, very likely to express A themselves, regardless of how many others may have expressed B. So there's a strong sequence dependence, as well as a dependence on just the raw number of A's and B's that they've seen before. But this changes quite radically in a situation where the connectivity is sparse. So what we see there is these contour lines, if you look in the bottom left heat map, they sort of collapse in on each other and they become parallel, showing that now the rational thing for the agent to do depends only on the difference between the number who've expressed A and the number who've expressed B. And these contour lines are very close together, suggesting that the response to any given number of individuals should be much stronger than it is in the fully connected network. And then if we condition on what the most recent decision is, we see that the pattern barely changes, except for the fact that we've obviously removed one part of the plot because they must have seen at least one A. Other than that, their response still just depends on the difference between the number of A's and number of B's. And sort of intuitively, this is because in a sparse network, the individuals that they see are independent of each other. So if I see you saying A and I see someone else saying B, there's no way that those two opinions are themselves connected to each other. And so I can sort of just count how many people have expressed each opinion, and it doesn't matter which order they did it in. So the main question that the paper addresses is, having calculated what rational agents will do in a sparsely connected world, what would happen if we then changed the connectivity of the environment they live in? And I'll give a couple of examples in a minute about exactly how that connectivity might change. So we're imagining agents who are adapted to a world in which they live on a sparse network. The people they tend to meet are treated as independent individuals. But then we start to ramp up the connectivity of the network while the agents still believe themselves to be living in a sparse network. And most importantly, I was interested in how they perform in terms of how often they actually get the right answer using the social information rules that they've learnt being habituated to this sparse environment. And so we can see that illustrated in two ways here, either in terms of the mean degree of the network that I put them in. So as I increase the connectivity, the mean degree increases, or in terms of the raw connectivity. So that's the probability that my individual is connected to any other individual in the network. So these are basically the same results, just illustrated on two scales. And what we see is for any given network size, you see here networks from 50 to 200, there's a clear optimum in the connectivity for those agents. So remember, these agents still believe that they're in a sparse network. They act as if they're in a sparse network. Up to a certain point, as I increase the connectivity, the agents get better at making decisions because they're given more social information on which to make those decisions. So they have more information about the world that makes their decisions better. But then at a certain point, that sort of collapses. And that's most clear perhaps in plot C, where you look at the connectivity. There's this rapid collapse as you approach a connectivity of 1, where everyone's connected to each other. And their decisions start to get much worse. And the optimum here scales in various ways with the square root of the network size. So what does this actually mean for the sort of networks of social individuals that we see in the real world? Well, one example we could think of is for animal populations. So animal populations worldwide, especially as I'm aware of in England, animal populations have collapsed over the last 50 or so years. And for social animals, this could be a catastrophe well beyond the fact that their sheer abundance has gone down, which obviously makes them less robust to further extinctions, to further changes to their environment, because it could also affect how well they're able to make decisions in the real world. So if, for example, they are habituated to a low connectivity, but not infinitesimal. So if I put them, for example, on this blue line, then they're making reasonable decisions about the world. Those decisions might be, for example, where are the food resources today? Where is a good place to shelter? Where are good places to nest? If I rapidly reduce the connectivity, then I simply remove a lot of the social information that they have available on which to make decisions. And so when those decisions are intrinsically difficult and they struggle to make them just as an individual, that's going to decrease the quality of the decisions they make. So they'll end up searching in the wrong places for food, trying to nest in the wrong locations, failing to adapt to changes in their environment, which that social information may have provided information about. If we look at human society, obviously we have different levels of connectivity in our world. We have close-knit networks of friends where we sort of know how people are connected to each other, and we know how to adapt the fact that, you know, person A, who I know, knows person B, so their opinions are not independent. But out in the wider world, we're used to a world in which if we encounter someone on the street today and they say something, and then we encounter someone else in a different part of town tomorrow, we don't expect that their opinions should necessarily be causally related. But as we increase in a modern society, transport, telecommunications, the density of urbanization, those assumptions start to break down. And initially, that can be a good thing because we're increasing the number of social connections everybody has. That's providing more social information for each individual. So if everybody's being rational, which, you know, we can speculate on how likely that is, then people should start to make better decisions than they were making before. So that's all to the good, and that's sort of, you know, the root of the optimism about collective intelligence in modern society. But if we don't adapt to the way that those connections are becoming more dense and more clustered, we can overdo it. So we might think about, for example, social media and the fact that we have ubiquitous internet connectivity in our pockets at all times, that everybody is aware of what everybody thinks all the time. If we sort of psychologically don't adapt to the fact that those opinions that we're seeing pumped at us on the internet all day are not independent of each other, we move into this world in which we've got this hyper connectivity. We start to treat people as independent when it's not appropriate. And therefore, we essentially get massive sort of information cascades where the initial decisions by one or two individuals cascade through the network as everyone follows each other far too strongly, and the quality of our decisions declines. So 2 quick takeaways from this talk. In the conservation of animal populations, I think we should think as much about the density and connectivity of animal populations. So density, how much they're interacting with each other, whether their habitats connect or whether they live in lots of different isolated habitats, as well as the raw abundance, the raw number of different individuals still alive. And in human society, we're all aware of the various pathologies that social media can have. I think we have a couple of options. We can either manage that connectivity. Who's going to do the managing? I don't know. But we can manage it to make sure that people are not overwhelmed by this torrent of information coming at them in a sort of, you know, in a social way. Or perhaps more reasonably, we can try individually to adapt our behavior to a highly connected world, to try and realize that when we observe, say, 5 people expressing an opinion online who to us seem disconnected, that behind the scenes there are probably social connections which are making their opinions highly correlated in a way that is not intuitively obvious to us.
Right.
And I just leave as a final point in the grey that I leave it as an empirical question whether people do that or not.
Fantastic, Richard. That was very clear and a good example of a sort of logical network analysis linked very much to some real world choices. If you have any comments or questions, do please put them in the chat or the Q&A. We will try and come to those at the end. If you could stop sharing, Richard, we'll now move on to Aleks Berditchevskaia from Nesta, who did an early paper in the journal sort of mapping CI research and AI. So Aleks, over to you. And if you could share your screen.
Great, thanks. I'm going to do it now. So let me know if you can see everything.
Yep, that looks good.
Okay. So Thank you. I'm going to be talking about some of our work on mapping the relationship between collective intelligence and artificial intelligence, and also a bit more broadly how this feeds into the work of the Center for Collective Intelligence Design, where I'm based. I'm going to try and stick really tightly to the 5-minute mark here, so I'll go really fast. Apologies, but hopefully you'll get a sense of what I'm talking about, and happy to answer any questions in the Q&A. So understanding how AI can help us enhance collective human efforts is at the heart of our work at Nesta's Center for Collective Intelligence Design. We're a team of designers, researchers, and technologists who are really focusing on creating new processes and digital tools that bring groups of people together in order to understand and act on big societal challenges at the intersection of health and environment. And so the origin of this piece of work was an initial mapping, a case study analysis that we carried out looking at the different real world applications that combine collective intelligence methods and AI. And what we were finding is that there were actually pretty narrow set of machine learning techniques that were mostly being used to analyze the kind of citizen generated data, mostly passively generated data. And so in order to understand if this rather narrow application of AI to collective intelligence was the result of the underlying research pipeline, we undertook a bibliometric analysis looking at the CI publications that had come out between 2000 and 2020, and specifically looking at the way that AI is starting to influence the field and the kind of overlap between the AI and CI literature, which I'll be calling AI and CI for the rest of the talk. So this is just a brief overview of our methodology. You can see the fully detailed pipeline either in the paper or on the GitHub repository. But I guess just to mention here, what we were trying to achieve is a more kind of larger scale quantitative analysis to complement some of the qualitative mapping that had happened previously to define different typologies of collective intelligence. And we were using Microsoft Academic Graph to collect our data. And by having this automated pipeline, we were hoping to look at the kind of broader high-level trends in disciplinary and topic diversity, as well as the contribution of the private sector and some early indicators of patterns of publication venues. So we collected over 39,000 collective intelligence only publications, and then 4,350 research papers that sit in that overlap between AI and CI. And so we can see that when it comes to that AI and CI overlap, it's a relatively small share of collective intelligence publications overall, about 13% in 2020, but this is approximately double what it was 10 years prior to that. And so there's a question that we were posing of, is AI and CI increasingly playing a role in the trajectory of CI as a field? And one of the questions that was brought up by our analysis is if we might start, as a result of that, seeing a narrowing of the field, because when we look at the kind of disciplinary breadth, it certainly seems to be the case for the AI and CI subsection of our data set that there is less disciplinary breadth over the last 15 years. And even though we see more disciplinary breadth for CI-only publications, there is an increasing influence of computer science. And when it comes to topic diversity, there are two topics that were really growing in prominence in our analysis, and those are crowdsourcing and machine learning, unsurprisingly probably. And we also saw alongside the appearance of new terms in the AI and CI overlap literature, which were supervised learning, training set, annotation, and even citizen science, which suggested to us that the real focus of that intersection between AI and CI is on using collective intelligence for annotation and training models, rather than perhaps what we might want to see of more of an integrated hybrid human-machine intelligence, as well as a more methodological diversity. So we can see there was a decrease in the representation of topics such as swarm intelligence and even distributed computing over time. And then the final thing I wanted to highlight is the relative importance also of the industry-led research in our data set. So we can see that since 2010, the AI and CI publications from industry have been increasing faster than non-industry publications. And the opposite is true for the CI-only publications in our data set. So there are other findings that I don't have time to go into because I'm trying to be strict, but I did want to leave maybe with a few questions. Sorry, Geoff, I'm going rogue and posing my own questions to the panelists. But I guess what these trends started to suggest to us is that if AI and CI literature continues along the same trajectory, might we miss out on some of the more creative combinations between collective and artificial intelligence, and also reduce the kind of technological diversity that we're seeing in AI R&D and the potential for a more kind of human-centric approach to AI. And so the two projects that I've highlighted on this slide are work that we've been doing in the Centre since we first carried out this mapping, hoping to at least try and buck some of these trends. So we've been particularly interested in developing new participatory approaches to the development of tools that use machine learning. And I can talk about a project either that we did last year with the Red Cross, where we were working with frontline workers and crisis-affected communities to develop new predictive models, or a recent project that we started, which will take place over the next 3 years, where we're working with partners to prototype new decision support tools that are based on a methodology that combines knowledge graph architecture, AI, and crowdsourced solutions from domain specialists in order to address open-ended problems in climate adaptation and health. So I'll stop there. Hopefully there's enough there for us to continue later.
Thanks very much, Aleks. And I would strongly recommend reading all the many other outputs from Alex's team. And I may sort of turn to all of the speakers to, at the end, perhaps comment on where you think the crucial sort of gaps in research might be in the next year or two to try and fill. Our next speaker is Eugene Vinitsky. I hope you are ready to share, who has an imminent paper for the journal. Yeah, slideshow. Fantastic. Over to you, Eugene. We can't hear you. Are you?
You're muted.
Yeah.
I'm muted. Hi, I'm Eugene. This is joint work between NYU and my colleagues at DeepMind, titled A Learning Agent That Acquires Social Norms from Public Sanctions in Decentralized Multi-Agent Settings. And I'm going to try really hard to keep the 5-minute limit, so I may talk a little fast. We are entering a really fun era where deployed multi-agent systems are becoming more ubiquitous. You could think about things like drone networks, but also going to a more transportation setting, thinking about, multiple map types like both, say, Apple Maps and Google Maps, and cruise controllers that are networked through vehicle-to-vehicle networks or things like that. The thing is that as we kind of move to these multi-agent settings in which we have multiple multi-agent systems that are not necessarily coordinated, we may need things like norms to achieve a shared desired outcome that is more than free riding. And I always think of this fun story where Google Maps wound up routing a huge amount of traffic through a tiny little town in New Jersey, creating 3-hour delays there, which is just an extreme example of free riding. The other thing is these systems are going to operate in human settings where the environments have existing norms that we need to reason and know about. So we want autonomous systems or agents that can acquire social norms. And the question in this work is how we get those agents to learn norms in large, partially observed games. So this is going to be critical to deploying agents in settings with norms. And we're also going to need to acquire these norms in kind of a decentralized fashion that's compatible with the way that these deployed systems might need to learn norms. So our work is going to focus on learning social norms. We're going to make a couple assumptions on the model of the model that our agents are going to use to learn those norms. So the first being agents are going to have their own internal model of norms, agents are going to learn those norms through observed disapproval. So we're going to assume that there's access to some signal over whether actions are approved or disapproved. You could imagine this as something like a Yelp review or a horn honk, something that is visible to you that society or the people around you disapprove. And we're going to assume that agents have weak preferences for obeying those norms. So they get some signal, they kind of want to obey it a little bit. We're going to mostly study this in this setting called allelopathic harvest. It's a fairly simple game where agents run around with this little zapping beam. When they zap some berries with a particular color, those berries change to the color of their zapping beams. The more berries there are of a particular color type, the faster that type of berry grows. So the goal here is for the agents to converge on a particular color type and all color it as much to be as much of that color as possible. But agents have diverse preferences over which color of berry they would prefer. So about 50% want red, 50% want green, no one wants blue. They also have the ability to zap each other, to sanction each other. And if you get zapped, that's a sanction, you lose some points for being zapped. The model we're going to throw at this problem we call classifier norm learning. So we're going to learn a classifier using a cross-entropy loss on global punishment events. So we're going to take all the data of observed zaps that we saw of ourselves and the agents around us. We're going to train a classifier on that, and we're going to provide, each agent has its own private classifier, and we're going to provide the outputs of that classifier at some layer of a neural network. And then we're going to add a small reward for aligning with the punishment events that the classifier predicts, and a small penalty for disaligning with the predictions of that classifier. And if we do that, I'm going to actually skip the slide. So we have this model, and what we're going to look to answer is whether this architecture enables us to learn norms. We're going to ask if these norms are beneficial, and we're going to try to understand how these norms are going to actually shape the learning process. So if you do this, you see this really nice event. What we have here is on the y-axis balanced accuracy, on the x the number of learning steps, and in green we have the when the classifier is on. In blue we have it when the classifier is on in a different game that I didn't mention, and in orange when the classifier is not on at all. And what we see is that turning the classifier on and adding this reward for aligning the classifier in turn makes the classifier more accurate. If we do this, we observe in these games that the agents converge to their equilibrium faster. They converge to a more beneficial equilibrium. So this plot is about how close they are to the equilibrium. Higher is better. And I think this is maybe one of the more interesting plots. We look at whether it is easy for agents to tell whether they are deviating from the group norm or not. So they have all these different colors, one of which is incentivized, one of which is disincentivized at the moment by the norm. And we ask, we look at the ratio of your likelihood of being sanctioned, given that you are a particular color. When this classifier is on, your likelihood of being sanctioned, if you are the non-dominant color, is significantly higher. It is easy for the agent to tell which equilibrium it should be playing. And I'm just going to go here. Then the last thing I should say is, so when this thing is on, the agents converge to a significantly higher reward, indicating that despite potential costs associated with being sanctioned and sanctioning and time lost due to sanctioning other agents, they're still kind of at a more beneficial equilibrium. Anyways, quick takeaways. So small amounts of publicly shared information on sanctions can improve multi-agent learning, and an internal classifier group approval with a small incentive to align with that group approval is sufficient to learn norms, at least in this game. So thank you very much.
Thank you. Thank you, Eugene. And yeah, and there's lots of applications of that we can all imagine, having cycled through a big city this afternoon. Lots of parallels in the real world. Thank you. Our next speaker is Simon Garnier. If you could take over the screen.
Yeah.
Thank you.
Can you see my screen? All good?
Yeah, that's great.
All right. So I'm going to be quickly summarizing today a review paper that I've written for the journal Collective Intelligence with my collaborator and long-term friend, Mehdi Moussaid, who's a researcher at the Max Planck Institute for Human Development in Berlin. And when Mehdi and I decided to write that manuscript, we essentially decided to target specifically young researchers in the field, people who are starting their career in the field of collective intelligence, and try to give them a sort of our overview of what the question of collective decision making is at the moment. So with that sort of target audience in mind, we split the paper in 3 sections, and I'm going to quickly summarize in that presentation. The first section is also the introduction, and we essentially spend that section trying to define what collective decision making is in the first place, knowing that both the word decisions and collective are pretty proteiform and can mean a lot of different things depending on the context. And so to sort of simplify our argument and the text, we decided to come up with a very practical and restricted definition of collective decision making in that context. And essentially, by practical, what I mean is that it has to be useful for making experiments in the lab, for instance. And we essentially decided to focus on decision processes that were meant to reach consensus or to build consensus, because consensus is a very convenient benchmark. And it allows also to consider the group as a unit, which is very practical if you want to do, for instance, evolutionary experiments. It's also a concept that is very friendly to apply different analysis from optimality and rationality theory. And we also limited ourselves to situations in which options are discrete, in the sense that no member of the group can benefit or suffer from the consequences of an option, of more than one option at a time. And this is also a very practical aspect experimentally, because it allows to very quickly and accurately measure the strengths of the consensus. Now, with that definition in mind, the second section, we decided to dedicate it to a very brief and completely incomplete history of the field. And in particular, we try to retrace 2 different paths, or 2 different disciplines that have studied the problem of collective decision-making. The first one, both like historically speaking and probably in terms of volume of publication, is social choice theory, which you can date back all the way to Condorcet in the 18th century, and which is mostly interested in understanding the relationship between personal interest and collective outcome on one hand. And it's historically been mostly focused on human collective decision-making. And the other field that studied a lot collective decision-making is swarm intelligence, which is where I come from originally. And the field is mostly interested in the behavioral mechanism. So how do we reach consensus in the first place, especially in decentralized system without central control? And swarm intelligence historically has been mostly focused on animal and artificial groups. And over the past 20 years or so, these 2 fields have pretty happily collided with each other and have formed a form of hybrid field now, where you can find studies that will use tools and concepts for both from both type of traditions, if you want, and give maybe a better comparative framework to understand more general rules about collective decision making. And then finally, the last part of the paper, which is also the longest one, we're trying to look at what's coming next, what are evolutions in the field that are happening or that we think should be happening. And we find 3, we sort of highlight 3 of them. The first one is a methodological evolution. We are starting to have access to tools that allow us to have extremely high dimensional data, and sometimes over multiple, more than 2 actually, levels of observation at the same time. And that will soon, or it is happening to some extent, allow us to link brain processes to population outcome in one single experiment. The second evolution, which is linked to the first one, is more theoretical, where we see that there is a shift away to some extent from this individual as particle formalism to a more process-based model, which will capture more intrinsic cognitive mechanisms, for instance, which make it also easier to integrate into the models the effect of learning and memory on collective outcomes. And then finally, the last one, which is a bit disconnected from the other two, but it's also very important, and Richard hinted at it in his talk, is this societal problem. We have these large-scale communication networks that are globalizing our social dynamics and making them hard to predict. And we spend that last part of the paper trying to discuss, are there better ways that we can regulate or help these mechanisms to avoid the negative consequences of these large-scale social dynamics. And I'm going to end this, hopefully within a 5-minute block, and with giving you all the information you need to find the paper online. It's been released open access thanks to Collective Intelligence, and so you should be able to get your hands on it if you choose so. Thank you very much.
Merci beaucoup, Simon. We will have, so I would again encourage, we have a very knowledgeable group on this call, so please do ask questions, make comments. We'll have a few minutes to discuss. And the topic I will try and get us to, which I think links all of these papers, is really where we go next in terms of research method of linking theoretical models and experimental models with the large-scale empirical data from reality. But we'll come to that in a moment. Marcin Waniek's paper is in a sort of parallel space. So Marcin, over to you.
Hello, everyone. My name is Marcin Waniek. I'm now with New York University Abu Dhabi, and I would like to present joint work with Cesar Hidalgo. And our work concerns building bridges in social networks. In particular, in networks where we observe a dissimilar homophilous communities. And I will model a network as an undirected graph. And in this network, we'll observe some kind of phenomenon spreading, some kind of network diffusion. You can think about this phenomenon, for example, as a new idea or as some new innovation spreading in this network. And at the beginning, only very small subset of nodes, only very small number of members of the network adopt this innovation or have this new idea, here represented with red nodes. And over time, this phenomenon spread over the network according to some rules. And our work is part of the literature analyzing what connections are important to spreading this phenomenon. For example, there is this concept about the strength of weak ties, in which the idea is that the crucial connections for spreading different kinds of network diffusion in social networks are actually the connections for acquaintances. Right, so the connections to people who maybe do not know many of our other friends, who give us access to like further away parts of the network. On the other hand, different parts of literature say that, oh, maybe more important for spreading network diffusion are actually having closely knitted groups of active nodes. This is particularly the case for complex diffusion. So diffusion in which in order to become activated, in order to acquire this new idea, I need many of my friends, many of my network neighbors to be active, to have this idea already. And in this work, we add another aspect, this setting. We assume that the nodes in the network are characterized with some attributes and that they may be more or less similar to each other, which causes that they will more or less strongly influence each other. In particular, in real-life social networks, we observe this phenomenon called homophily, which states that you are more likely to connect in a social network to people who are more similar to yourself. And this is a very, very natural property, very natural phenomenon. However, research shows that it might lead to formation of filter bubbles and echo chambers that may significantly hinder network diffusion, right? Because if all my friends are very similar to myself, then every idea that comes from outside of this closely knitted group of my friends might seem like an attack, actually. So the setting to be more precise, the setting that we consider is that we have a social network in which nodes can be similar to different degrees to each other. This similarity is represented by the thickness of an edge in this picture. And at the beginning, we have two separate communities. that are very closely knitted within each other, but that have very few connections between each other. And in one of these communities, some new idea emerges. So at the beginning, a small set of nodes in one of these communities become active. This is the seed set. And the questions that we try to answer in this work is, okay, let's say that I want to speed up the spread of this diffusion to the entire network. What kind of edges can I add between these two communities in order to speed up the diffusion, in order to boost this network diffusion? Assuming that I have limited budget, that okay, I can only add to this network very few network edges. So when we theoretically try to find the optimal way of solving this problem, we find that the problem is NP-hard, which translating from computer science into English means that it's basically impossible to solve it optimally. However, maybe we do not necessarily need an optimal solution. Maybe we will just be happy with a heuristic. So we analyze a class of such heuristics that, when asked to add an edge to the network, base their decision on two different factors. On the x-axis, we have average degree of the two nodes that we are trying to connect with this edge. So on the left, we will create edges between nodes who have very few neighbors by themselves. On the right, we'll create edges between hubs of these two communities, between very important members of these communities. And we also consider similarity between two nodes. So at the top, we'll add edges between nodes who are very similar to each other, in these two communities. And at the bottom, we'll add edges between nodes who are very dissimilar to each other in these two communities. And the color will represent the diffusion time. So the lighter the color, the better, the faster the diffusion from one community to another. And if we take a look at the results, these are results for complex diffusion. The crucial aspect of this boosting this diffusion, it actually turns out to be similarity, that you do not necessarily need high degree nodes, that adding connections between low degree nodes that are highly similar is in some cases the best possible solution of boosting this diffusion between dissimilar communities. Okay, so to sum up, we investigated this problem of building bridges between communities. Solving it optimally is NP-hard, is an exponential task. Connecting high degree hubs in these communities might not be the best idea. However, in many cases, connecting low degree nodes, but that are highly similar from these two communities, might be the best way of speeding this diffusion. And just to give you an idea of what other results we have in this paper, we also considered different levels of susceptibility to this diffusion. And we found that even a very small number of highly resilient nodes can greatly hinder the network diffusion. Thank you very much.
Thank you very much, Marcin. And I should say, often, I think in the journal, we're interested in non-obvious or perhaps surprising conclusions which come out. And in a way, it's a sort of slightly surprising line of argument. Do please, as I say, ask with any questions. There is one already in the Q&A for Aleks. Can I ask you each for a very brief comment on an application of all that you've said? I spent some of my morning with a group of head teachers, and one of the big problems of teachers in high schools now is, what do you do about misinformation, the spread of untruths and so on, which is socially reinforced? So maybe a sentence or two, can I ask each of you, this is very unfair, I know, how you would apply what you've presented to a case like that, which, as I say, certainly links Simon, Eugene, Marcin, and Aleks. It might be, what do you need in the algorithms they're using on social media to combine AI and CI to block misinformation cascades? Richard, is it fair to turn to you first for a comment on that?
I'll give it a go. I mean, I think I would have two very simple answers, which may not be of any great depth. I mean, the first is with my own kids, I will be keeping them off of social media for as long as humanly possible, I think, because I mean, I think people are not well adapted to social media, and obviously for children, it's in particular, like, they don't understand the mechanics of what's going on behind it. But I think schools could have a very important role to play because people are going to have to adapt to the fact that the information they perceive is not of the same nature as they instinctively imagine it to be. And so schools can play a role in educating people about, much like, when I was, 20 years, 30 years ago, doing media studies at school, and they tell you about how the media works and how, newspapers lie to you, etc. Now kids need to be told that on social media, it may not be a choice of people lying to you, but when you see 100 people saying something, it doesn't mean 100 people independently came to the same conclusion.
Yeah, exactly. Aleks, thoughts from you, and maybe you could also comment on the question, the Q&A.
Yeah, so I guess I was just thinking about a project that we did at the centre last year, where we worked with 300 teenagers in the UK to crowdsource the advertising they were getting on social media about unhealthy foods. And one of the outcomes, the key outcomes of that project, was that teenagers began to, or at least their self-report was that they really started to understand the targeting of certain advertising towards them. And I guess maybe what you could do is really work actively with teenagers to collect data about misinformation, and involving them in the process will then help them to kind of understand what they're actually seeing and become maybe better at discerning some of those cascades themselves. So I think that could be really interesting. Kids are very smart, and they, especially if you can create a fun interactive experience, I think that could be great to do. And then I guess on the question in the Q&A, I mean, maybe I should pass on to others and I can type the answer to Saffron in the Q&A, because I've got a lot of suggestions.
You got a lot to say. Okay.
Towards.
Good. Okay, Eugene, over to you.
Yeah, I guess the relevance of the work that I talked about today is that if you make public sanctions very observable, then learning algorithms can kind of reinforce on themselves and converge to whatever the current expectations around social norms are. And that's relevant in the sense that if you have really strong filters controlling the amount to which those social norms are observable, you can kind of change the type of equilibrium that's being learned. And I guess what I mean is really powerful filters on social media can have powerful consequences on kind of where you're getting to. And we don't really have these powerful.
Well, no, there's no sanctions at all at the moment to misinformation and spreading it. Zero, as far as I'm aware.
Yeah, so it would be really neat to see kind of tools for displaying sanctions for types of behavior on these systems.
Simon.
So I'm going to say I agree with everything that's been said already. Also, I think this is a question that doesn't have a definitive answer, but also sometimes I have the feeling this is and sorry for the one that are younger than me, but it's a discussion of all people, in the sense that younger people are already using social media in a way that's completely different from maybe our generation. And it's a bit maybe early to say that they are in danger of this social media. They will take over the social media and they will make it what they want. And they are already, I think, evolving, with quotes around evolving, toward filtering themselves out from these informations. I mean, I see this, I do these surveys in my class every year, and I see them first moving away from social media to some extent. 10 years ago, my students were all on some social media. This year, I have maybe half of the classes on no social media. And so I think there is going to be a natural evolution of population in response to what is happening right now. So
You're an optimist. Okay.
I'm an optimist, which is trying for a French person, I know, but yeah, I'm optimist that the next generation is going to do better than we have done with this.
Okay. We will need evidence as well as optimism. In a moment, if Panos, Jessica, or Scott would like to come in, please do. But Marcin, what's your view on this? Again, these sort of spreads, the diffusion of not such good ideas through networks.
Sure. Because so the connection between disinformation and potentially my work, I feel like the goal of many of these disinformation campaign might be sowing disagreements between actually different groups, different polarized groups. And applying my findings, well, I feel like in many cases, there was a service that was trying to serve, I think it was between Democrats and Republicans in the US. It was trying to serve you news from the other side of the barricade, let's say. And this, I would maybe compare this to showing you a very high degree notes from the other community, right? So maybe a very polarizing celebrities from the other community, which this research would suggest it might not be such a good problem. So a potential application of the heuristics that we found very successful in this very theoretical model, of course, would be maybe showing you normal people, trying to connect you to quote unquote normal people from the other side of the barricade, maybe showing that we are not actually that dissimilar to each other after all.
There is a very nice beer advertisement which does exactly that rather well. I think it's Carlsberg, precisely that method. Do any of the other editors want to make a comment at this point?
If I may ask a cheeky question to
Yeah.
Richard. Richard is scared now. At the end of the presentation, you say you want to leave it to other people to do the experiments to demonstrate your points. Why not you making these experiments for once? I would love to see you in my lab getting your answers from time to time.
You would not want to see me trying to conduct the experiment.
Well, maybe that will help you with your theories now.
Well, maybe I could generalize your question, Seymour, because the question I was going to ask you each to do 30 seconds on was, as I said a bit earlier, where do you think sort of research methods need to go to iterate between theoretical experimental models with agents and the empirical analysis of the real world in social media or classrooms or real urban landscapes? What might we be seeing? And you had a fantastic set of lists, Simon, of where methods might be going. So I might start with you to talk a little bit, and then perhaps a comment from each of the other speakers before we wrap up.
Well, I think the first challenge, we are in the sort of like, I think some people call this the sociomics age, where we're starting to have access to so much data about social information, how it's processed in the brain, how it's affecting different levels of complexity when you go up in the levels of observations. And I think the first challenge is going to be designing models and mathematical frameworks that can capture that very multi-level layers, knowing that there are feedbacks between the top layers to other bottom layers, which traditionally in most models that we have, which are emergent models that are bottom up, these feedback are not usually implemented. So I think that's going to be the first challenge, is as someone, maybe Richard, because he doesn't want to do the experiments, will need to come up with that mathematical frameworks that can capture that more complex, I think, nature of feedback loop between these levels.
Yeah, and that's a great answer. In social science, is largely missing actual models for complex adaptive systems at multiple levels with feedback loops down as well as up. Richard, thoughts from you?
Yeah, well, I mean, just to follow on from what Seymour said, actually, I mean, he told this sort of anecdote about his students in his class who've grown up with social media, and I think we should be studying that more systematically. How do people deal with social information who have grown up with it? I mean, my intuitions about social media are, like Simon, those of someone who grew up in a completely different world where, we didn't even have email when we were kids. And it may well be that people who are young are already adapting, and that many of these sort of assumptions about how people adapt to change may be irrelevant if people can adapt very quickly. So I would love to see some systematic studies saying, what do people believe as a function of what they see on social media, perhaps as a function of age as well.
Fantastic. Eugene, any thoughts from you?
Yeah, I think that we're missing, that I think would make this all really exciting, is if we had more kind of synthetic systems that we could use to study these in scale. So no one said the word large language models yet, so I'm going to say it. But really large, like social media-like environments populated by synthetic agents, possibly large language models that we can use to study these questions in kind of exciting empirical ways and deploy targeted interventions and things like that and see what that does. So I'm really excited about kind of more powerful tools for studying these questions.
And are you going to do that?
I'm thinking about it.
Okay. Marcin.
Sure. So from a network science perspective, so as I said, this work was purely theoretical, partly because we had a lot of problem with gathering real life data with enough granularity. So it's reasonably easy to find a very large social network, but not so easy to find a network when we also have a lot of information about each of the nodes, and also we have a history of some kind of diffusion in this network that we can then build the model. So I feel like having methods of kind of scaling this bottom up, parameterizing the theoretical models with real life data in settings where we have access to very limited set of real life data, that would be really, really helpful.
And what might that have been? Would that have been Twitter data or Facebook, or what other sources might there have been for an empirical version of your model?
So the idea that we try to apply in different works, so that to have a large structure of a network taken, for example, from Twitter or from Facebook or from whatever, and try to have some kind of diffusion model on it, where the probabilities of the diffusion, like deeper inside the model, are created based on the answers of some kind of smaller survey of people. So I think this kind of, we tried this at some point, it did not work very well, to be honest, but I think these type of methods, I think, might have something in them for the future.
Great, thank you. Aleks, you put a bit in writing in the chat, but maybe say some of it briefly, verbally, because it's very interesting stuff.
Yeah, of course. So I shared a few links to publications we've put out, some of the AI and collective intelligence real world examples that I think are particularly interesting. One of the publications that I linked to is a report we published for the Collective Crisis Intelligence Project, and particularly a project that I highlighted is one called Sentry Syria, which has developed a predictive system to warn communities who live in conflict zones about upcoming air raids, and they work with volunteers on the ground, as well as remote sensing technology in order to have that as inputs into the algorithm that they update regularly. There's a few other links in there. I mean, I do want to come back on this methodological question. I think some of the stuff I'm really interested in is looking at how we might develop new methods for deliberation at scale that are actually effective. So I think citizens' assemblies have received a lot of attention in the last couple of years, but they really seem to be the only model, and they don't have, they don't take advantage of the kind of advances that we've made in terms of developing digital technology. So I'd be curious if we can maybe have more of a mixed methods approach, which combines crowdsourcing, deliberative polling, in-person deliberation, and what that might look like. And when it comes to modeling, I think the incorporation of lived experience data and behavioral data into those models is something that's really important, as well as then bringing them out into decision-making contexts where you are having different stakeholders actually interpret some of those results and reflect on how that might impact the kind of choices that they're making in the short and long term. So a set of methods I'm interested in are called participatory modeling, where that happens mostly in relation to climate adaptation. And I think that might help us to start to make this better link between, you know, understanding the world and then actually leading to action in the world.
I'm going to have to cut you off, Aleks, because we are unfortunately out of time, but thanks for those comments. Thank you all for contributing your papers, and to the other authors who have and are contributing to the journal. I think it's pretty clear, even from this discussion, the freshness, the dynamism of thinking, this interaction of theory and practice, models and empirical work, I think makes me sense, exactly as Aleks said, we're still in the relatively early stages of a new science, a new set of disciplines, but ones which will become, I think, immensely important in the in the years ahead. So we will finish now because we're just over time, so I failed in my basic duty, but hope to see all of you again, and we'll have more, I hope, discussions and debates and arguments about both methods and results in the future. Thank you very much, and have a lovely rest of your day, everyone.
Thank you,
Thank you.
everyone.
Bye.
Bye.